Greetings all. Stop recording. Sorry, Dad. All right. You're here. I'm here. Take a look at this graph over here. I would just like to give you a little bit of a precursor to what you're going to do in your project tomorrow, although we have all day tomorrow to talk about it. But more importantly, just to give you kind of a little warm up as to kind of something that we can now do. And I just want to make sure you kind of see the big picture. In a sense, this is what you're going to do for your project. You're going to come up with some cool looking red curve here that's some, cooler than any curve you've ever seen. Ideally, something that no human being has ever seen. And then not just find the slope of a point on the curve, but find the equation of the tangent line. And not just do that, but do it for, well, every point. Like, can you make it slidable? Notice this will take you 2 seconds to check yourself to see if it's working. Notice everywhere I go, everywhere I drag the slider, it's staying tangent to it, and it's going to take me 2 seconds to grade it. And it's kind of hard. It's kind of hard to grade in the sense that if it's tangent, you get 20 out of 20. If you don't, if it's not tangent, then now what do I do? Like I don't want to give you nothing because you put some time into it. But it isn't tangent, which is the whole point of the problem. And so don't turn this into me until it works. Like, bug me, I'll help you. But this is what should happen to it. Now, the reason I'm showing you this now, because we'll talk about this again tomorrow, is because I want you to understand kind of something cool that may come up in a later class. It turns out calculus is a prerequisite to other classes, and it's a prerequisite to harder physics. And I teach statics and dynamics, and one of the things we study in dynamics, which was just so cool for me to learn, I never realized how this worked before, is just how motion works. And so I mentioned this a little bit the other day, but if let's just pretend this red curve is a road, and we're driving down the road. And so if we're driving kind of, oops, that's not right. If we're driving kind of in this direction, this tangent line in a sense represents where your headlights would be pointing at any given time. But in terms of how motion works, how particles fly through space, just in terms of understanding how motion works, it turns out that vector, or that arrow, if you will, that's pointing tangent to the curve is the direction that your velocity is going. So if you're going 60 in your car, that's the direction you're going. You're going along that tangent line. Now, 1 second later, you're now going a totally different direction. Does that make sense? You're actually aiming at a different direction. So you're only going that for a billionth of a second, ultimately. So it's really hard to understand like how motion works. But to break it down and make sense of it, ultimately what mathematicians have figured out and physicists have figured out is that no matter where you are on this curve, you're actually on a circle. And you know that this equation is a lot more complicated than a circle. And yet it can be simplified down to just being a circle. And notice if I get really close to this, then that red curve, at least from here to here, could be thought of as a circle with a certain size radius. And notice where I am on the curve right now, I don't know, where would you guess? I mean, this actually looks reasonably like a circle. I'd say the radius might be right over here somewhere. But does it make sense if you're up here, you're now on a much bigger circle. So you're on a totally different circle. But ultimately, mathematicians have figured out a way to kind of understand motion based on two things: the direction of your velocity. And so that's your velocity has a component that's your gas pedal in a car. It's like how fast are you pushing the gas pedal? But it also has another component and that is the perpendicular component. So what you experience is what mathematicians or physicists call centripetal acceleration, is when you turn your car really sharp, you kind of feel yourself smashing against the door. And really, this direction, which is perpendicular to the slope, is the direction effectively of your velocity that you're changing your direction. There's a velocity of just your gas pedal, but then there's also a velocity associated with, hey, I'm going to turn now. And the direction of that vector is actually pointing toward the center of that circle. And again, what's so cool is 1 second later, the center of the circle has moved. I mean, this, as I said, this red graph is not a circle. So you're on a circle, but the center of it actually moves because you have a fairly small radius circle right here, but you have a fairly big radius circle maybe up here. And if we go way down here, obviously that's a really small radius circle. And if I'm over here, that's a really big radius circle. And so you can actually, even though this isn't a circle, you can actually understand how motion works at any given point. Well, kind of like we do in calculus, there's a lot of different slopes here, but you can find the slope at any point. And so you can figure out what's going on in terms of your velocity, what part of your velocity is directed toward getting you to go faster along the red curve, and then what part of it is you changing directions. And you may understand that there's a lot of centripetal acceleration in this corner because you turn really sharp. You're really going to smash against the wall there of your car. Whereas here, that's a pretty gradual corner. So you're not going to slam as hard into the wall of the car, the door of the car in that location. So it turns out both the normal curve, or the normal, which is code for perpendicular. I think we've ran across that a time or two already. The normal is important and the tangent is important. And so if this logic makes sense to you, if you do take a class later than this, you'll kind of go, oh, that's cool. I'm using this stuff now. And actually the normal is not that hard, because if the slope, well, let's go turn the slope back on. Let's say that green slope right now is, I don't know, let's just keep it simple. Let's say it's like a fourth. If you did calculus and you got that the green slope is a fourth, you should remember what to do to get the blue slope. You don't have to redo any calculus. What do you have to do to 1/4 to get the perpendicular slope? Somebody tell us.
Do you do the equation of the tangent line?
Easier than that. I'm saying if the green slope was the fourth right there, what do you do to a slope to make it perpendicular?
You just flip it, yeah. Reciprocal. I don't know the word.
Yep. I love both those words. You take 1/4 and you flip it over, so now it's 4/1, and then you change the sign. So if the green slope is positive 1/4, then the blue slope would be -4. You flip it and change the sign. So flip is reciprocal and negative is inverse. Those are the technical words for it. So the blue slope would be -4. And so it actually is not hard. You don't have to do calculus again. You'd use calculus to get the tangent slope, and then you just flip it and change the sign to get the normal slope. And both of those things help you ultimately understand, what's happening to that particle as it flies along this really crazy course. And of course, what's kind of neat about what we just learned is you can now come up with equations that do really crazy things. And so this is kind of cool. And maybe just because you're curious, I'll show you really quickly, because again, this is just some equation I made up. Notice it's ax cubed minus by squared minus c sine of y equals d. And I didn't even put constants in front of those. Like I can actually drag mine around. I found like the slope. I found like the tangent line for a whole class of functions, you might say. And then I can slide along kind of to any point. Every place I go, I have, again, I'm only interested as far as you don't need to understand the perpendicular slope. That's not something we're talking about right now. But basically, I have a tangent line that works in any location for any equation that's even remotely the same.
I have a quick question.
Go ahead.
So about the circle thing, where you can think of any place on the line is actually part of a giant circle. What about inflection points?
That's a great question. Everybody understand what she's saying? Would you agree right here, the red curve is concave down, which means the circle's like down here. And then when you get over here, all of a sudden the circle's concave up. That point right there would be an inflection point. That's the transition. Would you agree the slope right there is perfectly flat? Just for a second there, it's perfectly level. Well, if it's flat, then is it a part of a circle? The answer is kind of no. Well, I guess you could say it is, except for the radius is infinite. So that's a very insightful question. So yeah, if it doesn't have some concavity to it, then it's kind of like for a second there, the circle goes away, or I guess you could say it has an infinite radius. So you're right. That's not simple, and that's not obvious. Good question. So anyway, all of that is just to kind of motivate, our study really today. I just want to practice. I don't, as I said yesterday, I don't really have anything new that I need to teach you. But it takes a lot of practice to be good at the chain rule. You might want to consider doing the odd problems in 3.7 in your textbook if you know you need more practice with chain rule. And same might be true for this section in 3.8. You might need more practice than kind of what we're doing in class. I'm trying to sort of give you the chance to gain conceptual understanding of this by talking longer about less questions, if you will. But you'll probably need more practice. And I think if I don't want to just ramble, without any explanation. I want to kind of go slow so that you're reasoning about it. So let's do something just to kick it off, kind of from yesterday. Let's do something like this. So yesterday I gave you something that was an ellipse, and it kind of looked like this. And we're going to do something kind of cool with this just to save a little bit of time and make this a little bit more interesting. But I don't know, I'm just making this up. Let's say 5x squared plus, 12y squared equals something, except for let's throw one more term into this, like a 4xy into this. So my question to you is, and you should know the answer to this, but like, what's that going to do? Like from yesterday, the 5x squared and the 12y squared would seem to indicate this is an ellipse, but what's going to happen if I throw a 4xy in there? Is it still going to be an ellipse? Or is the 4xy going to totally transform it into something completely different? We'll look at this together. And then I'm just going to say this is equal to some number. But before I say it's equal to some number, I'm actually going to make sure this goes through a point. I want this to go through a point. So I'm going to make that point up right now. Let's see. What should I do? I think I'll make x to be -2. And I don't want it to be too big. Maybe I'll just use 1 for y. So I want this to go through that point. So rather than just making a number up on this side, I'm going to make it up so it goes through this point. So if I plug -2 in, let's see, that'd be 20. If y is 1, that'd be 12. So I'm up to 32. And then this would be 4 times 2. This would be -8. So I guess that's 4. It's 24. So if I made this equal to 24 now, oops, that's not what I wanted to do. If I make this equal to 24, then I actually know it'll go through that point. So what I want you to do, and I'm going to give you some time to do this, is see if you can find the slope. Can you find the slope at this point? To me, this is a good test question. It's not some crazy equation with signs of x cubed y squareds. And, in a sense, if you get good at this, I could give you anything and you could now take its derivative. But it's like, let's not get carried away. I mean, the test should be pretty straightforward. Let's see if you can get this right now from yesterday.
Is that equals 24 or equals 2y?
24. And we'll graph this in a second and kind of check it. And this is the kind of thing you should be doing on a test.
Would the slope be 1?
So Caesar weighs in, thinks the slope is 1. I'll give everybody else time to
Yeah.
see if they agree with that. If you agree with that, say so. Or if you say I got 9 or whatever, say it, and we'll do it together in a second. But
I got -4, but I don't know if I did it quite right.
I love it. I'm hoping we'll get 6 different answers. If we all get the same answer, that means we're wasting our time because we already know this, right? So I'm hoping we get a number of different answers because we should be fixing our thinking.
Yeah, I got -24.
Yes. 3 people, 3 different answers. I'm happy you guys are making my
I
day.
got 8/11.
4 different answers. Oh, yes. I'm so happy right now.
I don't know if I'm right. I got +5/4.
Yes. Oh, this is great. You guys are making my day. Well, here's a hint in that direction. We said the point was at -2. That's not a negative sign. Get some glasses, man. So there's the point we're at. So that should tell you something. You should be able to look at that and see about what you think the slope is. Let's see.
I got 1 too.
Oh, 2 people get 1. Oh, we finally got 2 people that agree. That's good. I just hit zoom square because it zoomed kind of weird. So if you didn't get something positive, that's not good because that's certainly a positive slope over there. And it would be around 1. I mean, I'd say that kind of makes some sense. So I'm going to take this over to our screen. So I'd say a slope around 1 looks pretty reasonable for this. What I don't want is for you to not understand whatever mistake you made here. So anyway, let's launch into it. So one of the keys to this question is just to say, okay, good. I've got some X's and I've got some Y's. And so what I'm really doing is I'm finding dy dx. In other words, I'm finding the derivative with respect to X. And so when I see X's, I think, good, that's what I've always done before and what I understand really well. So you should say, awesome, the derivative of 5x squared is actually 10x. Now, if you're starting to get confused with chain rule, fine, but let's think about this. It's really 5 times junk squared. So isn't that 10 times junk times the derivative of the junk? That's what chain rule says, except for isn't the derivative of X actually 1? Because we're taking the derivative with respect to X. Then I can take the derivative of X and I get 1 for that. And so as we did before, we say, okay, the derivative of 5x squared is 10x. But 12y squared is not so easy because of the chain rule. So I say, okay, great. The 2 first. So it's 12 times junk squared. So the 2, because of power rule, comes down front, multiplies by the 12, and it's 24. The junk doesn't change. But it's then times the derivative of the junk. But see, the difference here is it's not 1. The derivative of y, well, you look at the equation back here. If you were to solve that for y, that's a complicated equation. So the derivative of that equation, if I solve that for y, would not be 1. Like it's big and ugly. And so really I'm wimping out here and saying times the derivative of y, well, that's The derivative of y prime. And then what do you think, what are you thinking when you get to this step, the 4xy? There should be something that goes, aha,
Product rule.
product rule. You should be looking at thinking junk times junk. Product rule. Doesn't really matter where the 4 goes. I'm just going to give it to the x. And so product rule says the derivative of 4x, which is 4 times y left alone, plus 4x left alone times the derivative of y. What's the derivative of y?
Y prime.
It's the derivative of y, which we write as y prime. So that's the product rule happening right there. As a simple check, anytime you see a y in a problem, there better be a y prime. Meaning, hey, look, there's a y, y prime. Hey, look, there's a y, y prime. And then the derivative of 24 is 0. Again, quick reminder, why is the derivative of a constant 0? Well, the derivative, remember, is always finding slope. And if you're looking for the derivative of a line that's 24, you're talking about y equals 24. So that means that'd be a horizontal line where all the points are y is 24. Hey, look, that slope is 0. That's why the derivative of a constant is 0. It's not just, you should have questions of that nature, you know, as you begin to think deeper about this. And so now I just have to solve for y prime. And so I look at those terms that have y primes in them, and I'm very, if you will, excited to see these plus signs. So there's actually 4 different terms there. 2 of them have y primes and 2 of them don't. And so I just need to get all the y primes alone on one side. So I'll just leave the y primes over here. So there's one of them, and I'll leave the 4xy prime over here. But then I got to get rid of the other one, so I'll have to subtract 10x away and subtract 4y away. And now I can factor y prime out, or as I like to say, just undo the distributive property. That would leave 24y and 4x behind. The other side is unchanged. And then I have y times junk. So to get rid of it, you do the opposite of multiply, which is divide. So again, I think this is the way you should feel on a test. I think I'm right. But now let's go figure out and check it as compared to the graph. Let's figure out what y prime of -2, 1 is. So let's see, that would be -10 times 1 minus 4 times, oops, I'm already screwing up. That's why you need to write stuff down on a test, because if you put 1 there, I'd be teasing you, like, what are you doing? X is -2. Y is 1 over 24 times y, which is 24 times 1, plus 4 times x, which is -2. So let's see, I get 20 on the top minus 4. So 20 minus 4, I think, is 16. And then 24 minus 8, also 16. So yeah, if you said 1, I think you're right. And that does agree with the graph. And so now I'm reasonably sure that I got it. So a whole bunch of you weighed in, good for you. And with all kinds of different answers, like, did my solution tell you what you did wrong? Like, are we done? Or you should maybe have some questions like, well, why did you do this? Or why did you do that? Or whatever. Like, make sure the goal here is not to watch me do this. I already know how to do it.
I just failed at algebra.
Yeah, it's an algebra mistake. No problem. Who cares?
Yeah, I just didn't do the product rule for some reason.
Yeah, super easy to do. Yeah, you don't see x times y as a product rule. Yeah.
Could you simplify down your equation at all anymore?
Good
Because
question.
I'm thinking maybe you could, but I'm not sure if I'm doing it totally right. Like if you divide 4 out, but 4 wouldn't go into 10. So
Yeah, the key is distributive law. So you're not going to get rid of any x's and y's. Do you see that? Resist the temptation to say, oh, look, there's an x and there's an x. I'll cancel those.
Yeah, no, I'm talking
No,
about,
I know you're not doing that, but
yeah, I'm talking about the numbers themselves.
yeah. So for instance, could you divide the top by 2 and the bottom by 2? Notice there's enough numbers there that they all divide by 2. Could you even do 4? Well, you can't do 4 because 10 doesn't divide by 4. But could you divide the top and the bottom by 2 and get negative 5x minus 2y over 12y plus 2x? Absolutely. Yep. In this case, that didn't save me much time, like plugging the numbers in. It's not that much easier, but you know, anytime you can, it's always good to do. Let me just show you one other interesting thing before we leave this. Is there any other points this goes through? Let's see. There's a suspect. To me, that looks like it goes through. Now you got to think about this a little bit because of the scale of the graph, but what would that be? 1.2? And then y would be negative 1.4. Is that true? Does it really go through that point?
We don't know.
And might somewhere near it.
Certainly near it, but my guess is it probably doesn't. And the only reason I say that is notice there's a bunch of squaring going on. So I don't know, it might, but it's definitely close. In other words, and I'm not going to take the time to do this, but if I put those two numbers in for x and y on the left-hand side, if it's not equal to 24, which it might be, it's going to be darn close to 24. And the only reason I'm saying this is on a test, for instance, I might not make this up. If I did make this up and say, I want you to find the slope at a point like negative 2, 1, then I would make it up in exactly the way that I just did. But many of the questions we're going to tackle today, there is no exact point. You can't even find one. As soon as you throw sine in there, for instance, now there's no exact answers anymore. And so all I want to say is that point is close to working. And even if it doesn't work, it'll allow me to check my answer. Would you agree that should be a small positive slope? So even if this point does not work, I could go down here and throw 1.2 and negative 1.4 in. And just expect to get some kind of a small positive slope. So I'm not gonna write it all down, but I am at least gonna quickly type it in. Let's see, parenthesis negative 10 times x, which we said was 1.2, minus 4 times y, which we said was negative 1.4, close parenthesis, all divided by, start a new parenthesis on the bottom, 24 times x, which is 1.2, plus 4 times y, which is negative 1.4. If I typed all that in right, then wonderful. I got negative, I'm embarrassed to say, negative 0.27. That's not good, because isn't the slope a small positive number? Now we already checked this, so what I'm guessing is I just did something stupid and I typed into my calculator wrong, so I'm just going to take a quick look at that. So yeah, I mixed them up. On the bottom, it's 24 times y, and I put 24 times x, so I was dumb. But I'm never personally, I don't know if you will, I like to do that stuff with you live because I want you to not be afraid of making mistakes. People think, you know, you're supposed to just get this stuff right all the time. Like you should be making dumb math mistakes. So I did it a second time and I got 0.22222. So now I'm feeling like, hey, good, it worked. It checked. And maybe you recognize that's actually 0.2 repeating, it's 2/9. So I got the slope of 2/9 there. So that may not, as I said, that point might not even be on the graph, but it's close enough to being on the graph that I should be able to use it to check my work. Okay. So
I have a question.
Yeah, please.
So I'm struggling a little bit with the vocabulary. So
Yeah.
what we just did is finding the tangent line at that given point, right?
Yeah, we really found the slope at that point. But I'm definitely going to ask you to do that. So let's go on and now even find, and this was my next plan anyway. Let's find the equation of the tangent line. Not just the slope. And let's do it at the exact point, the one we know for sure, -2, 1. So armed with the slope, maybe I'll, instead of using M, I'll just write the word slope. Armed with the point -2, 1 and the slope that was equal to 1, thanks to our work back there, that's not a hard equation to write. So most of calculus problems, you're just finding the slope at a point, the derivative. So you could find the derivative in general. We found the derivative here, and that's an equation that, as I said, is kind of like a slope recipe. It tells us what we need to find the slope at any given point. And then we actually found the slope at a particular point, -2, 1. And now we're going to go even one step further and find the equation of the tangent line. So again, my logic is the easiest way to do this is to stick the slope in where it belongs and then say, oh, the point X is -2, Y is 1 has to be true because the line goes through that point. So that'd be 1 equals -2. The only way that happens is if B is 3. So all of that says that I think my equation is Y equals X plus 3.
So I do this differently than you. I find it really confusing whenever I use B. So I plug in Y minus the Y value equals the slope times X minus the X value.
Yep.
So is that's the same thing, right?
Yeah. So let me just say a couple things about that really quick. I like mine because I know what lines look like and I don't have to memorize anything. You're memorizing something. But where what Eve just described comes from, and the way this is sometimes taught is, isn't slope equal to Y minus Y over X minus X? Like, isn't that what slope means? And so if I come back and say, hey, I know the slope is 1. And hey, I know that Y was 1. And I know that X was X minus -2 would become X plus 2. Like, you're starting with not what I'm starting with, which is kind of I know what the generic equation for a line looks like. Now notice I have to memorize that. This person is saying, I'm just going to memorize the equation for slope. Eve's example is actually just taking the X minus X and multiplying it up to the other side. So you have X minus X times the slope equals Y minus Y. I don't care how you get the line. Whatever way makes sense to you or whatever way you were taught, I think is great. I don't care, as long as it works. Again, what's cool is in Desmos, you could be done right now. Like, type that into Desmos. It doesn't look like a line. And that's the advantage of, what I'm describing back here. Like, this is called slope intercept form because of all the forms. This one tells you, hey, look, the slope is 1 and the y-intercept is 3. Like, you can get a lot of information from that, whereas you can't get that information from other kind of weirder lines, weirder versions of the same line. So then, just to satisfy ourselves that we didn't blow this, hey, look, that really does look tangent to the curve. So we just did a whole bunch of work and got it to be at 1 point. And really tomorrow's project is, could you even let that point slide? Could that -2, 1 not be stuck at -2, 1? Could you actually come up with a letter there, like A1 or AB for your point, and then let that slide around, and then you found all the tangents instead of just one of them? I mean, that's kind of cool. But make sure you're using Desmos is the key, just because you should not be getting this wrong and not know it. Okay. What I'd like to do now is some time I've spent, and then also some students that I've had in the project that I just gave, came up with some pretty fun looking implicit equations. And really all I want to do is just practice with a few of these with you. And so I had some kind of fun with this, if you will, nerd fun, like this equation here, 4xy plus 5xy squared plus 4x squared equals 16. That's not terrible. There's no e's in it, no signs in it. Notice there's a whole bunch of chain rule, and there's a whole bunch of product rule in it. But notice it kind of came up with sort of a cool looking, I don't know, I thought it looked like a bulge. So I called it the bulge. Do you know your anatomy and physiology? Here's a graph that has sine in it, x squared plus 4x plus 3 sine of y plus 5. Notice the y, notice that's a sine wave, but it's vertical because it's not x, you're not taking the sine of x, you're taking the sine of y. And yet the x squared apparently kind of made two of them. So it's like two sine waves. I mean, isn't that kind of cool? Looks like a colon. So there's the colon function. Here's the parabolic sword. Amazing. I mean, it's just cool graphs. Like when you do this project, if you're not having fun, you're doing something wrong. Like this, you should be playing around with this. And again, what's kind of neat about it that I mentioned yesterday is you're probably making equations or graphs that no one's ever seen before. I mean, it just feels cool somehow. So I just want to play with some of these. So let's start with this one, the parabolic sword. What I'm going to do is I'll post all of these. We won't have time to do all of them, but I just want to give you time to try to tackle this. And before you even do that, let's go down here on the graph and can you appreciate that there is not going to be any x's and y's that make this equal? Like there's no whole numbers I can stick in for x and y. This is not going to be equal. So let's go to the graph and pick a point that looks like this goes through. And I just want to make a point to you. Do you think it goes through that point right there, 1, 1? It looks like it, but that's really dangerous. And why do I say that's really dangerous? Well, because
we don't know for sure if it goes to that point, right? Because we
Yeah.
don't know if the graph is set to that point.
That's right. But still, it's okay to estimate. But the problem is what if we're off and it's actually up here? Does it make sense? That gives us a really steep slope. But then what if it's off by just a little bit? Now all of a sudden it's over there. That's a really dangerous corner to miss it by. You see what I'm saying? Again, this is just interesting. Whereas this point right here, that one, it may not go through that point either, but that one's not dangerous. Do you understand what I mean by that? If we miss it by a little bit, is that going to screw the slope up? I don't think so. To me, that looks like a slope. Well, that looks like about a slope of -2. Notice what point is it at? What's the coordinates of that point? You can't just look at the boxes. What's the coordinates of it?
Isn't it 0.5, 0.5?
Yeah, 0.5, 0.5. So all I'm saying is let's do the same thing. Like check your work here. Check your work. If you put in the point 1/2, 1/2 or 0.5, 0.5, do you get kind of a steepish negative slope? Even if it doesn't go through that point, it's darn close. So I'm just going to shut up and give you some time. That's a little harder, right? But I'd like to give you enough time that you know you're wrong or you know you're right. The question is, will the parabolic sword stab you or will you wield it? I'll give you a second. like I know. Feel free to chime in, like if you come across something, or you can say, I took the derivative of cosine of 6xy and I got this. Is that right? You can ask me those questions.
Yeah. So I've got the derivative. Now I'm just trying to algebra out the y prime. I got a negative sine 6xy times 6y plus 6xy prime equals 4x minus y prime, and I'm trying to isolate the y prime on the left side.
Yeah. The algebra to isolate y prime is no joke on this question. So if you haven't gotten where Vale's at yet, take a stab at it. Like, see, even if you get it wrong, let's talk about it. This is an algebraically fairly challenging question. All right, I'm going to catch up to you with respect to the derivative. If you're going to get chain rule figured out, you've got to get good at doing one thing at a time, like ignoring stuff. And what I mean by that is when you see this, you should be saying cosine of, well, stuff. Like, I'm just going to ignore that for later. The outer function here is clearly cosine. So that's the first thing I've got to deal with. This is how chain rule works. So I say, what's the derivative of cosine of stuff? Well, derivative of cosine of stuff is negative sine of stuff. Now chain rule says times the derivative of that stuff. And that derivative is not simple. You can't just look at it and go, oh yeah, there's the derivative. What should you be thinking when you look at the derivative of this expression? One of the rules should be jumping out at you. Which one?
Product rule.
Product rule. So that's almost like a whole separate side problem. So let's see, what's the derivative of that stuff? Well, the derivative, again, I'm thinking of the multiplication sign is right there. Derivative of 6x y prime. The derivative of 6x is, I'm sorry, yeah, the derivative of 6x is 6 times the y left alone plus the 6x left alone times the derivative of y. So all of that is multiplied. Ooh, that's terrible. Derivative of cosine of junk is negative sine of junk times the derivative of the junk. Other side, much easier. Derivative of 2x squared is 4x. The derivative of y is the derivative of y.
I got it.
So I'm just going to rewrite this and then start kind of what Vale's question was, which is now what? This is a place where if you're sort of lazy about the way you write things down, you might miss it. What's wrong with what I just wrote down?
You're missing the parentheses on the 6y plus 6xy prime.
Yeah, like you're multiplying by all of that stuff. That's really important. Like in a sense, you could be lazy and not write it down as long as you knew that it was everything. But with respect to this class, like I got to grade this, and more importantly, you might screw this up. And because that's a parenthesis, does it make sense this sine of y here is actually getting multiplied by this plus this as well? I mean, if I was to multiply it, maybe I don't need to multiply it, but that's important not to screw that up. Now, your job now, because calculus is done, your job is just to find out what y prime is equal to. It's just algebra. And in an ideal world, you'd be awesome at algebra, and this would be like, okay, I'll watch TV while I finish this. It's super easy. But this is really tricky, and I guess I want to give you some logic to this. The only way you're going to get all the y primes on one side is to add them to one side and then subtract away the non-y primes. But notice in the order of operations, this multiplication right here, in the order of operations, you have to multiply before you can add and subtract. Like I need to add and subtract to get everything together on the same side. And notice in the previous problem, we didn't have to worry about that. It just happened automatically. But this problem, there's some multiplication to do. And if I don't do that first, if I say, okay, cool, I think I'll subtract 6xy prime over to this side, like you can't do that because you're going out of the order of operations. There's some multiplication to be done, and you're just saying, I'm not going to do it. I'm going to skip it. You're doing the order you're doing the order wrong. You broke it. So you actually don't have a choice here, amazingly. You actually have to multiply this out. So if I multiply 6y times the sine of 6xy, there's that. And then I do it yet again, multiplying by 6xy prime, and I get negative 6xy prime times the sine of 6xy. Doesn't it feel like you must be doing something wrong? Like this is getting worse, it's getting terrible. And so now that I've done the multiplications, now I'm free to do the additions. And so again, what I'm looking for is, hey, look, there's a term with a y prime and there's a term with a y prime. I need those all to be on the same side so that I can factor the y prime out, so that I can undistribute that y prime. Now that the multiplication's done, I can collect them on the same side. Should I collect them on the left or the right? Should I move this one over to that side? Or should I move this one over to this side? What do you think? Well,
Wouldn't you want to add? Oh, sorry.
No, go ahead. I was wanting an answer.
So wouldn't you move it to the right since you want to add the whole thing?
Yeah, like maybe you're like me and you don't like negative signs. And so when you see this plus, when you see this negative, you think, oh, cool, I'll add this over to the other side. Now it's over here. So over on this side, I've got 6xy prime sine of 6xy. I just added it to the other side. And then there's still that minus y prime. And then here's a 4x. And so I need to subtract it over to the other side. So I guess, unfortunately, what's over there is a bunch of minus signs. But it ultimately doesn't matter. Like you can collect it on either side and it doesn't make any difference. Either one will work just fine. But you actually get the two answers you get, depending on which side you pick, are going to look a little different. And so we'll talk about that when we get there. But now you're kind of home free. But man, you got to be good at algebra not to blow what I just described. Now you can say, hey, look, these both have a y prime. So I will undistribute them. Notice that leaves a 1 behind. It's not gone. It leaves a 1 behind as a placeholder. And then, of course, this side just stays the same. So let's copy it. And then I just divide and I'm all done. So if I divided that to the other side, man, this is the best. Oops, that's wrong. So this is a really ugly slope. So if I divide that to the other side, then of course it's going to be over here. So then I can say y prime equals all this junk. Probably don't need those. So I don't know about you, but if I'm alone doing this, I look at that and I think, God, I don't know. There's no way I got this right. Like, even if I know what I'm doing, I probably made some mistake, even if it's just a copy mistake, like I lost something, lost a y someplace or whatever.
Yeah, I got some signs different. So my top side is completely positive, but then I have negative nonsense plus 1 instead of positive nonsense minus 1.
So you're saying you got positive signs on the top
Yeah.
for both of them. And then your 6x was negative.
Yeah. And then +1.
And then your y was positive. What's your thoughts on that?
So the reason I did that was because I had the negative y prime, and then I had inconvenient negatives on the left side, so I just changed all the signs to positive because they're more convenient.
Yeah, if you collected it, like I chose, if you will, just sort of randomly, or actually because of one of your suggestions, I chose to collect all the y primes on the right-hand side. And so that produced my answer. Had you collected the y primes on the left side, you would have got this second answer. Do you see that they're the same? What algebra would you have to do to these two to show they're actually the same?
Just multiplied by -1, right?
Yeah, if you took the top and erase this, but if you took the top of this and multiplied by -1, and you took the bottom and multiplied by -1, you just get different signs. And so see, when I'm grading this, I got to be careful, right? Because my answer key might have the blue and red answer, and yours might have the green answer, and it's just as right. So if every sign is different, then you got it right. And if some of them are different, you got it wrong. But if they're all different, then effectively they're still exactly the same answer. So it might look a little different, but it actually, in a sense, does make a difference if what side you collected on. You might get a different answer than your friend or whoever you're working with. So they're both true. Good question. But of course, I'm not super confident just yet. So I want to go back and figure out what y prime of, let's see, yeah, it seems easier to type 0.5 than 1/2. And I'm also a little afraid that I'm going to just type this in wrong, right? Like even just to type that in your calculator is really legit. If I'm going to type this in my calculator, I'm going to need an extra set of parentheses around the top and the bottom to make sure that everything on top gets divided by everything on the bottom. But I'm going to attempt to type that in now. And I'm hoping I get some slope like -2 or something like that. And then I'll kind of know that, well, maybe I didn't get this wrong after all that. So that's kind of a miracle. So I won't bother to write all this down, but thankfully they're both the same number, like they're both 0.5. So parenthesis -6 times 1/2. Well, hey, I can do that in my head. I'm just going to say -3 times the sine of 6 times 1/2 times 1/2 times 1/2 times 1/2 -4 times 1/2. 4 times 1/2 is 2. Close the parenthesis, divided by, open another parenthesis. 6 times 1/2 is 3. That'd be 3 times the sine of 6 times 1/2 times 1/2 -1. And now I'm holding my breath. Oh man, I hope this is right. I got error. How does it happen so long? I look back at what I typed, and one of those times I managed to hit a 5, but the 5 didn't show up. I got approximately -2.5. I'll even write out some of the rest of it. 5056, and it goes on from there. So I look back up here and I think, hey, good, I got it right. Notice I guessed it'd be -2, but it's a little steeper than that, but it's in the ballpark. So yeah, I probably got it right. I won't take the time to do this, but if you put 1/2 in for X and Y, would those two be equal to each other? That's how you tell if that point's actually on the curve. But as I said, it actually doesn't matter if it's on the curve. It's just close. I'm just trying to check my work. So my guess is those are not equal, because cosine of a number is weird, right? Cosine of 6 times 1/2 times 1/2, that's going to, cosine of that number is going to be a crazy decimal. And on the other side, it's 2 times 1/2 squared minus 1/2. Like that's a fraction. I don't think this is they're not going to be equal. I can already tell. I didn't think about it till just now, but they're not going to be equal, but they'll be close. I would encourage you to type that in your calculator and see, oh yeah, they are close. They're close to equal. That's because this point is close to being on the graph. But it still served its purpose. I checked my work. And I'm going to do this on a test to save you some time. I'm going to give you the graph. If I come up with some interesting equation, I'm going to give you the graph on the test, and I probably won't say check it at this point. I might do what we did at the start of class, which is design the equation so that it actually goes through a point. And then I won't just say check it. I'll say find the equation of the tangent line through that point, and then you can check it that way. But on a problem like this, if I said just, find the derivative of this, then I probably will give you the graph. So if you have a few extra minutes, you can do what we just did and go check it. Well, let's see. What should we do now? Probably got time for at least one more. Seems like we should try the one that's got E in it, and plus it's Halloween, so let's get Dracula involved. So this one's got E and sine. It's only got one X in it, but it's got two Y's. And again, notice that it's just isn't it a crazy graph? Like, and in my case, I found this one and it was just by accident, if you will. I was just playing around, just throwing in, this is what you should do for your project, just playing around, throwing in weird stuff. And all of a sudden it's like, wow, that's kind of crazy. And this pattern continues, by the way, it just goes forever, left and right. It's just like teeth forever.
Is there a good way?
Go ahead, Felix.
Is there a good way for like people to predict what it might look like with all these crazy things in it, or is it kind of just random?
Question. The answer is not really. Like in your algebra class, you learn to predict that y equals x squared, no matter what else is there, looks like a parabola. Like if you have y equals x squared and then there's like a plus 7x or a plus 9x, the x squared is the dominant term. And so you said, hey, if it's an x squared, it's a parabola. And so you really just learn that by experience. And so the same would be true here, but it's just you'd have to practice. I can't even imagine how much you'd have to practice. Like there's so many options. Like what if that wasn't e to the y, but e to the sine of y? Like there's just so many things you could do to it that I'd say the practical answer to your question is no, like it's impossible. I think it's particularly fun when it creates a closed graph instead of just kind of going off forever, even if it's weird. This bottom one's really fun, but it just goes off forever in both directions. I think it's particularly fun when somehow it like closes back off again. I mean, that's just crazy, but that's a great question, Felix. I don't know how to do it.
Yeah, I just remember in like algebra classes and stuff, it was pretty impressive to me when we could tell what every little number was changing.
Yeah.
But for this, it's kind of just feels random.
Yeah. What you have to look at is this is a class of equations. And if you notice there's a 1/2 in front of the e to the y, and there's a 1 in front of the y, and there's a -10 in front of sine, you could mess with those numbers. And that's one of the things that's really fun about this. You can mess with those numbers and get a whole class of equations. And maybe if you messed with those, you wouldn't get this closed teeth anymore. A lot of times with these graphs, it's not simple. Like it isn't just going to make bigger and smaller teeth and they're going to move around a little bit. Like they might open up and not even be teeth anymore if you change that 10 to a 5. And so this is maybe a very particular graph that lives inside an entire family of graphs. And so, yeah, that's what I'm saying. This is like Narnia, like you're opening the door to a completely different world here that's just kind of much larger than the world you used to live in.
And you couldn't even really, it would be really hard to like graph that by hand just by plugging in points. Like if you started at x is 0, y is 0, x is 1, y is, because you could end up with places where it doesn't even touch those.
Yeah, notice this graph doesn't even exist somehow when x is 1 and when x is 2. So if you tried x is 1 and x is 2, it's going to say you can't even do that. There's not even a graph there.
I have a question.
Yeah, go ahead, Eve.
It doesn't really pertain to this, but would it be better to ask this question after class? Because it kind of doesn't pertain to this exactly, but kind of does.
Ask it now, and then we'll answer it after class.
Okay. So if I have an equation, but instead of setting like cosine to x or something, I set the cosine to theta, would you still be able to find the tangent line with theta? Or
Yep, you would. And I wanted to say one more thing about the answer to your question, Eve, is complicated. But yeah,
because theta equals radians or degrees. But how would you plug that in for your tangent line?
And that's something we'll go into. That's actually we're actually going to answer that in Calc 3, maybe 4. I think it's 3. But you may remember there's equations called polar graphs that create these cool leafy looking patterns to them, and they're real neat looking. And these are really random what we're doing right now, but yeah, any graph you make, you can find the slope of it. But it's in Calc 3, like take some more knowledge. But again, one of the
Okay.
things I'm amazed at, just to say one more thing about what Cheyenne said, is like, we were not able to see these graphs until 10 years ago. That's the thing I think is amazing. Because if you decided you wanted to graph this, it would take hours, because you don't know when you set out for this, you know, that X can't be 1 and can't be 2. And you'd have to find at least 100 points to say, I think I see what's happening here. Like a parabola, you only need to find 5 or 6 of them, and you're like, hey, I think I see what's happening. I found the graph. But these graphs are so complicated, it would take forever. And then just as a side note, it could be done with this problem, but you want to pick Y first. Like if you pick Y to be 2, notice the only thing left is sine of X. And so if you could get it, now that you chose Y to be 2, notice Y can be 2, then you would get it all, you'd get it down to where it said sine of X equals number, and then you'd go inverse sine and you'd get an answer. Well, you don't get an answer, you get millions of answers, and that's why the graph has a whole bunch of places where Y is 2. But you could do it. You could actually graph this by hand. Just so cool. Should see lots of points this goes through, or at least it looks like it does. I doubt it goes through any of them, but it looks like it does. Just going to give you one more minute and then we'll launch into this. I found a few points that I thought looked pretty good. Maybe you steal one of those and check your work. Where'd Lee stick off to?
Brian wasn't sleeping.
Oh,
Take him home.
tried to put him down. He didn't go.
Are your kids working now? Students? Or not kids, students?
Yep.
I have kids. You have students.
All right, let's launch into this. I doubt you did this, but remember this is an equation and you've got to take its derivative. And I don't know about you, but I don't like fractions. So I see that 1/2 over there and I think, hey, I'm going to multiply both sides by 1/2. I doubt you did this, and it doesn't matter if you didn't, but it's just kind of think about these kind of things. If you look at an equation and you think, oh, that's ugly. What if you think, I don't like minus signs, so I think I'll add that 10 sine x to the other side, and then it's all only plus signs. Remember, if this wasn't just sine of x, but it was also like times y, it'd be minus all of those things, and you might screw up the distributive law because it's minus and you didn't distribute it to everything. And so just think about the fact that you can do some creative things. And so in my case, I'm going to multiply both sides by 2 before I start. Because I'm thinking, oh, I'll probably make less mistakes now because it's all whole numbers. So, you know, what do you do every time? Well, we're going to take the derivative of both sides. But again, remember what it is, what we're doing here. We're really taking the derivative of both sides with respect to x. So the derivative of e to the junk is e to the junk. But what does chain rule say?
Multiplied by the derivative of junk.
Exactly, multiplied by the derivative of the junk. Equals the derivative of 2 times y. Again, you might be thinking, oh, the derivative of 2 times y is 2. No, it's 2 because it comes along for the ride times the derivative of y. I mean, look at the equation back here. This is a really ugly equation. If you solved it for y, the x's that would be on the other side would be, it'd be huge, it'd be gigantic. And when we're taking the derivative with respect to x, so the derivative of y is not simple. It is not 1. It is ugly. As I said before, the best way to, well, I'll save that for a second. And then minus 20 comes along for the ride, and then derivative of sine of x is cosine of x. So fortunately, that was just sine of x. It wasn't sine of x squared. It wasn't sine of the square root of x. So I didn't have any more to do. But just to check my work, hey, look, there's a y, there's a y. Do I see a y prime? Yes, I do. Do I see a y prime? Yes, I do. Every time there's a y, there's going to be a y prime. That's chain rule. Good. Okay, cool. Now I just have to solve for y prime. This time, all the multiplication has been done. All I have to do is collect everything on the same side. So again, it doesn't make any difference what side you collect it on. So I think I'll just move that over to this side for now. So let's see, I have ey times y prime minus 2y prime. And then that negative 20 is left over there. A lot of negative signs. Maybe I should have collected it all on the right side and I wouldn't have as many negative signs. Or maybe I just say, hey, before I even do this, I think I'll multiply both sides by -1. I mean, you're just doing algebra, so those are all okay. But now that I've got all the y prime terms on the same side, I can use distributive law and take them out so that there's only one of them. And so I think I'm done when I say that this is the answer. Again, your answer probably doesn't look exactly the same. You probably have a 10 on top and you still have a 1/2 right here. And then that 2 is probably a 1 because you didn't multiply both sides by 2. Fine. It's not like you had to do what I said. But remember, before you plug numbers in, if there was a 1/2 sitting down here, like couldn't you multiply the top and the bottom by 2 now and then get rid of the fractions? Just be good enough at algebra to be a little bit creative. So I think I'm right. I mean, if this is a test question, you just say, hey, find the derivative of this equation. I think I'm done. But I want to check my work. I don't know. I want to be sure. So let's see. Let's pick a point up here. Whoa, where'd you go? You're way up here. There you are. So I don't know. I'm going to pick that -3, 2 point. Looking at it right here, it looks like that's a positive slope. I don't know, maybe 2, maybe a positive slope of 2. I don't know. Maybe I didn't draw that accurate enough. Now that I look at it, I don't think it's very accurate. Maybe tangent looks more like that. That's a little better. Now that I counted, I would say that's down 3 and over 1. So maybe the slope is more like 3. Again, I really don't care. I just see it's a reasonably sized positive number. And so I'm just kind of hoping when I go down here and put in -3, 2, that I get a slope about like what that graph would predict. So y prime at -3, 2 would be, I'm going to write this whole thing out, -20, because I'm afraid I'm going to screw it up. Cosine of -3, all divided by e to the y, that'd be e to the second, e squared minus 2. Now I'm holding my breath, hoping that I get something that matches the graph. I plugged all it in and I got approximately 3.67. So a second ago, I estimated that to be about 3. So I'm thinking, check, I got this. I think I got it right. It was positive, wasn't it? Yeah, it's positive. So a little more than 3. Fine. So I'm pretty sure I got this right now. I'm willing to bet on it. And remember that -3, 2 is not on that graph. If you plug that in, it's not going to be equal. It's not on the graph, but it's close. Oh, they froze. Are you on something?
But me being on something shouldn't make them freeze, but no, I'm looking on my computer.
You're back. So I saw you guys freeze, which is a problem at my end, but I saw you freeze, so I didn't say anything else. You didn't miss anything. But are you happy with that check? Are you? So we don't have time to do another question, but I'll post all of these. If you want to play with them, you certainly can. But I think what I've illustrated is you don't need me to make these up. Like, get on Desmos and make your own up. Because you can check it. Now, you can't ultimately cheat in Desmos and say, what is the slope at 3, -2? It doesn't have that capacity. It can do f prime of x, meaning you actually have to have it solved for y. Desmos can cheat with that, but it can't cheat with this. But you can still kind of check your work. And again, the cool thing is we're still going to be practicing this tomorrow. The project that we're going to take on tomorrow is just you practicing this, except for you are making up your own and you're trying to get the point to slide everywhere. You're not trying to just find the point at 1 or the slope at 1 point. You're trying to find it at all of them. So we'll pick it up there tomorrow. All right. This is a rare day. It's 11:17 and I actually got you out of class early. So stay after if you want to ask me some more questions. But it'd be smart, since tomorrow's Thursday especially, to try to do the 3.8 assignment completely tonight. And I've actually given you way harder problems here than are in your homework assignment. My hope is that you'll think the homework assignment's relatively easy. But if you do that, then tomorrow while we're working, because in a sense, I'm just going to be here to answer questions while you guys play around with every single one of you playing around with your own question. You can say, hey, I got number 7 wrong, and you can ask me questions about it during class. So. What questions do you have for me?
So I missed yesterday's class. I'm assuming the project is something like you make up a formula and then you find a slidable point.